project, we worked on building and training a simple convolutional neural network or CNN to classify images from the CIFAR dataset. Throughout this video, I will explain the project step by step, covering the dataset, the model, the training process, testing, and results. And by the end of the video, I think we will get a clear view of this project. So let's dive in. So ma'am, I have done the project on PyCharm. As you were seeing, under the DIP lab folder, there's another folder called CNN CIFAR 10 where I have created the whole project. So in this project we have three Python files which are called CNN CIFAR 10.py, CNN model.py, and utils.py. Three of the Python files are dedicated for specific tasks. So now first let's start with the CIFAR 10 dataset. What is this actually? So this is actually the foundation of our project. CIFAR 10 is a widely used dataset in machine learning and computer vision. It contains almost 60,000 color images, each measuring 32 by 32 pixels. These images are evenly divided into 10 classes, such as airplanes, cars, cats, dogs, and to name a few. This dataset is split into two parts. The first is 50,000 images, which are actually used for the training and teaching the model, and the second is about 10,000 images that are used to testing to evaluate how well the model performs on unseen data. The small size and balanced nature of the data should make it perfect for testing simple neural networks like the one we are building in this project. Now, if we talk about the project structure, the project is organized into three main Python files, as I have already said. The first one is utils.py. Here it is, the utils.py. And in the utils.py, this file actually contains the utility functions, including the code to load the CIFAR 10 dataset and pre-process it. It also includes a function to visualize the images. And second, the CNN model.py. Here we are seeing the CNN model.py. So in this file, it defines the structure of our convolutional neural network. And the last and final is CNN CIFAR 10.py. This is the main script where the entire workflow comes together, from data preparation to training, testing, and saving the model. This folder structure also includes directories for storing the dataset and the trained model, ensuring that the project remains clean and totally organized. Now for the data preparation part. So we prepared the dataset using the prepare data function from utils.py. Here it is, prepare data. So here's actually what happens is, first we apply transformation in the dataset. The images are converted into PyTorch tensors, and their pixel values are normalized to fall within the range of -1 to 1, as you were seeing. I have commented it out here. This step ensures that the data is scaled properly for the model to process. The dataset is then divided into training and testing sets. So training and testing, two sets are different, using the PyTorch data loader. So after data loading, the data loader helps us load the images in batches, which is efficient for training. We also have a function to visualize the images. This helps us verify that the dataset is loaded correctly and get a feel for the images we are working with. So now, for how have we built the CNN model or convolutional neural network? So let's talk about the CNN, which is the heart of this project. The CNN is defined in the CNN model.py here actually. So, if we talk about the components, the first is two convolutional layers. These extract features from the images such as edges, textures, and patterns, and many different kinds of things. The second is max pooling layers. These reduce the spatial dimensions of the feature maps, making the model more efficient and less prone to overfitting. The third is three fully connected layers. This takes the extracted features and make predictions about which class the image is actually belonging to. The fourth one is softmax activation. So this is applied to the final layer to convert the raw output into probabilities for each class. This model structure is well suited for the relatively small CIFAR dataset and ensures the balance between simplicity and performance. Now for training the model. So once the model is defined, the training process begins in the CNN CIFAR 10.py script. Here is the CNN CIFAR 10.py script. So now here's actually what happens if we describe it step by step. The first one is device selection. The script checks if a GPU is available for faster computation. If not, it falls back to the CPU at first. And second is loss function. We use cross entropy loss, which is commonly used for classification tasks. It calculates how far the predicted class probabilities are from the actual class levels. The third one is optimizer. We use stochastic gradient descent (SGD) with a small learning rate and the momentum to update the model's weights during training. The fourth one is training loop. Their model is trained for 100 epochs, as we are seeing here, the number of epochs. During each epochs, images from the training set are passed through the model. The loss is calculated and the model's weights are updated to minimize the loss. and the running loss is printed at regular intervals to monitor training progress. By the end of the training, the model has learned to classify images based on the patterns it has seen. And now, testing the model. After training, it's time to evaluate the model on the test. So here's how it will work. The first step is the test images are passed through the trained model. For each image, the model predicts the class with the highest probability. The third is these predictions are compared to the actual levels to calculate accuracy. In this project, the model achieves an accuracy of approximately 74.5% plus, meaning it correctly classifies 75% of the test images. This is a solid performance for a simple CNN on the CIFAR dataset, as we have done, I guess. Now for the saving and reloading the model, once training is complete, the model's parameters are saved to a file named CIFAR10CNN path. This allows us to reload the model later without returning it from scratches. In this script, we demonstrate how to save the model using torch.save actually. So here it is, and reloading the model using torch.load. This is particularly used for deploying the model for performing additional testing. Now for visualizing prediction, we also visualize the model's prediction on a batch of test images. Using the plot images function, we can see the test images alongside their predicted class levels. This provides a clear, intuitive way to assess how well the model is performing. So this is about our whole project. Now if I demonstrate the project about how it is working, so we're going to run the cnn cifar10.py file. So I'm running it and it is executing. It will take a lot of time, as I have down here the batch size is 32 and the number of epochs that are going to perform is 100, so it will take a lot of time. The project is running and we will get the results. The batch size is 32 here, so that means we'll get 32 files. So as for the thing here, that I have already downloaded the CIFAR10 dataset, I mean the 60,000 images that we need for the project, so it didn't take time. So now we are seeing some pictures here in a grading system. So as I have mentioned that 32 the batch size will be, so 32 images are presented here. So I will just cross it for the time being. So now the main part will begin. It will train my model, and then after completing the 100 epochs, as I have told here, it is going to see me the result. It is going to help me get the results. So now it is working on the first epoch. So I'm going to fast forward the video from here. So basically, ma'am, our epochs have been done, our 100 epochs. So this is figure 1, and we are going to compare with that how our model has predicted the outcomes. This is a test set, and this is another one, which is the result set. And these are the images that it has predicted. So now let's see. So on the terminal here, if you turn it big, so as there were 32, so let's check this. So this is the prediction set, and that on the upper one is the actual test images. So let's see. For frog, it predicted frog, truck, deer, automobile, bird, horse, sheep, cat, deer. But here horse, and it predicted deer, and here it's again horse, but it predicted deer. So it's a failure for the horse prediction. Bird, truck, wrong. Truck, sheep, this is also wrong. Truck, cat, bird, but frog. Frog, deer, cat, frog, bird, truck, frog, cat, dog, but it predicted truck. Deer, airplane, truck. So our average accuracy is 0.76184, which is actually in percentage. If we convert it, it will be at 76.184%. So this is all about our presentation, ma'am. Thank you.